Hi and welcome back to this new video. We will continue with the transient response of first order circuits. This is example 10. We will continue with the RL circuits, and in this case we have a situation with two independent voltage sources, VA and VB, and we have three resistors, R1, R2 and R3, and there is a one inductor given. So these are the values for the circuit parameters, and what we need, what is required, is the current through the capacitor, through the inductor, and the voltage across the inductor as a function of time for time larger than 0. So the procedure is exactly the same as in the previous examples, so I will start right away. So what we have is, first situation is, look at the situation when the switch is open, so there is no change. And that's in this situation we have only this part of the circuit, so this branch is actually disconnected, so we can redraw this part. And actually what we always did for the inductor is, in steady state, or if you wait for a long time, the inductor behaves or can be modeled as a short circuit, so I will also emphasize this to calculate the required value. So what we have is the VA in series with the R1 and then the R3, and the inductor will be modeled as a short circuit. The current flowing here in this part of the circuit is the current for the inductor as the initial value. So the initial value I0, IL at time 0 is the VA divided by R1 plus R3. So what is that? That's actually 10 divided by 20 plus 30, and this will be 200 milliamps or 0.2 amps. So this is our initial value. Okay, so the next part is the situation when the switch is closed, and again that's actually always what we do. We will look at the situation when the circuit is again settled. There are no transients, so the steady state condition is again in place. So what we have is, this part of the circuit will be connected, so that we get a new branch, and the inductor is again a short circuit. So let's redraw this and make this clear for our next calculation. So the VA is in place, so we have the resistor R1, we have the resistor R2, and the voltage source VB, and we have the resistor R3, and we have the inductor, which is modeled by a short circuit. Okay, the current flowing in this situation is the final value of the inductor current. That's actually also required to calculate or determine the IL as a function of time, the expression for the IL. I will denote this point, this node, as X to carry out the calculation. What we need is, again, this. And there are a number different ways to determine the inductor current, final value of the inductor current. What I will do is use source transformation in this part. So what I mean by that is, I will use this. This is actually a Thevenin equivalent circuit configuration. I will transform this into Norton, and I will also transform this Thevenin circuit configuration to the Norton. So I will have a current source in parallel with a resistor, which is the R1, and I will also have a current source in parallel with a resistor, and in this case it's R2. So this is actually the current the source transformation, which is known from the Thevenin and Norton transformations. So what we have, I will do this to the next to the right. So what we have is this. I will get a current, and I will call that IA, in parallel with R1, and we have also the current source IB, which is in parallel with R2. That is actually the source transformation for the branch in the middle. And still we have the R3, and we have the inductor, which is modeled as a short circuit. So this is still in place, so this is not changed. So we have still the inductor current as a final value. This is the point X, so that is actually the same. So what you can say is, what is the benefit of doing this? So what we have now is a situation where we can add these two currents. So if I have two current sources in parallel, I can add them together and make an effective one current source. And I have also two resistors, R1 and R2, and now I can also make a equivalent resistance of that, and it will also simplify the situation for further calculation. So I will do that. I will denote the effective current as Ix is equal to Ia plus Ib, and the resistance the equivalent resistance I will denote as Rx is equal to R1 parallel to R2. But what is Ia and what is Ib? We haven't calculated that yet. For source transformation, you might know from Thevenin and Norton equivalent circuits, Ia is equal to the VA divided by R1, so that is actually 10 divided by 20, and it is 0.5 amps. And for Ib, I will get VB divided by R2, and it is 24 divided by 60. I will get 0.4 amps. So this is actually very straightforward. What you have is you have a voltage source in series with a resistor. You do the voltage divided by the resistor which is in series, and it's actually the same procedure here. So if I fill the given values here, what I have is 0.5 plus 0.9 is 0.4, and I will get 0.9 or 900 milliamps. And for Rx, these are of course the same resistance as this will not change. So Rx, and this is also R1 times R2 divided by R1 plus R2. This is actually the formula we have used many times. So what you get is 20 times 60 divided by 20 plus 60. So the net effect of this is 15 ohms. So I will redraw the circuit again to make the situation again clear for further calculations. So what we get is the new circuit with a current source Ix in parallel Rx, which is 15 ohms, and connected to that is the R3. And again, we have a short circuit model of the inductor, and this is the current we are looking for. And this is the point X. This point is still intact. Okay, what we can do now to calculate IL at the final value is use the current divider rule. So the current divider rule. So the current divider rule. And how does it work? If you want the current through this branch, what you do is, if you have of course two resistors, that is mandatory, you look at the other resistor and divide by the total resistors, the value of the total resistance, times the value of the current which flows in this node. So I will write it down in formula form. So we have is IL at infinity. The final value of that is the other resistor is the Rx divided by the total resistance, so Rx plus R3 times the Ix. So what we have is 15 divided by 15 plus R3 was 30. So I will get 30 times 0.9. So what we have is 0.3. And this is actually our steady state value, final value. Alright, so that's actually the whole story about the steady state value, which is a considerable work in this case. So what we do is now, the next step is a time constant. So we can use for the time constant this circuit. And again, we disable all the independent sources, and we'll look at in the terms of the inductor. So I will do that time constant. So what we have is I will redraw the circuit. So this is an open circuit. That's for the IX that will disappear. What we have is the RX, which is now actually in series with R3. And there is an inductor here. I will just show this to emphasize that there is an inductor which is looking to the left to calculate the Thevenin resistance seen by the inductor. So what is the tau, or what time constant for the RL circuit? Is the inductance divided by the Thevenin resistance. So what is the Thevenin resistance? The Thevenin resistance in this case is the series combination of the R3 and Rx. So our Thevenin is 30 plus 15 is 45 ohms. And finally, tau is then the inductance, which was 75 milli, so 0.05 divided by 45 ohms. So that will bring us to, in an exact form, 1/600 seconds. And if you approximate this, this will be 1.667 milliseconds. Okay, now we have all of the parameters required to set up the equation for the inductor current IL. So I will do that next. So the inductor current, what is that? That's the IL as a function of time, is IL final plus IL initial minus IL final times e to the power minus t divided by tau. Now let's fill in the values we have calculated. IL at infinity, the final value of the IL was 0.3 plus the initial value of the inductor was 0.2. So that's actually the initial, and then again the 0.3, and then e to the power minus t divided by, which is actually 1/600. So if I write it down like this, e to the power minus t divided by 1/600, and I will simplify this. What we get is EL is equal to 0.3 minus 0.1 e to the power minus 600 t amps. That's actually the expression for the current. So what is actually the inductor voltage? That's actually very easy, because once you know the inductor current, you can calculate very easily the inductor voltage using this formula. And we have seen this several times in the previous examples. So the L is given, we have already the expression for the IL, and we can differentiate that, and we have the value for the voltage across the inductor as a function of time. So this is 0.075 times the derivative of the expression 0.3 minus 0.1 times e to the power minus 600 t. So what we get is 0.075. Now differentiate this between the parentheses, what you get in 0.3 will be 0, of course, that will be left out, and then minus 0.1 times minus 600 will be plus 600, and then times e to the power minus 600. So it will be 6t times minus of e to the power minus 600t. That's what we get. And if you simplify this further, you get 4.5 times e to the power minus 600t, and that is actually in volts. And that's actually the expression for the inductor voltage. Okay, let's draw again the picture for inductor voltage and inductor current. These are the inductor current and inductor voltage. So let's do that. This is a sketch. We have the time, we have the inductor current, we do that in amperes, and we have the inductor voltage, and we do that in volts. I will draw the inductor current in red, and I will do that inductor voltage in blue. So what we have is, if you look at this carefully, and I will also denote the time and the value. At time equals 0, this will be 0.3 minus 0.1, that will be 0.2, and it will grow to 0.3. So what we have is actually the following. So it will start at 0.2, and it will grow to 0.3. So what we have is, this is the level, so actually it will start and then it will grow to this value. So this is the IL. Okay, now I will do the inductor voltage. Inductor voltage starts at 4.5 and it will reach 0 when the time goes to infinity. So actually I will start here. Again, this is two different time y-axis in one, so be careful when you treat this. So what you get is you will have a situation like this. I will draw this again to make this more clear. So this is the voltage across the inductor, and that's actually the whole story about it. So inductor current and inductor voltage, the complete picture will give you the situation. Alright, now that's actually the example for this case with the RL circuit having two independent sources, and we have calculated the current and the voltage. Now I hope it's also helpful with this example for you. Just follow this steps again. If you have problems, just let me know in the comments section. I will try to answer them as soon as possible. Thank you very much, and don't forget to share and to like. And see you next time.